In this lesson, we are going to learn assurance. So, assurance is a lump sum cash flow given to the policyholder in the event of death, maturity, survival, or surrender. Okay, and it is also based on the contingent event. Contingent event means the probable event that may or may not happen. For example, the termination of a policy in the form of a termination expense. Termination expense. Now there are several types of assurances. So let's look at a few of them. So the first one is whole life assurance. So as name suggests, if you buy this policy, your whole life will be assured. So suppose you buy the policy at age X, so from here your whole life will be assured. Now depending upon the type of payment, there are two kinds of policy. So the first is end of year of death policy, and the second is immediately on death policy. So suppose you buy the policy at age X, and in between X and X plus 1 you die at this point. Okay, let's say, so if the policy is immediately on death, then your nominee will get the money right at this point. Okay, and if the policy is end of year of death, then nominee will get the money at X plus 1. All right, now let's look at term assurance. So in this assurance, suppose you buy the policy at X and the term is n years, so this is X plus n. So within this duration, if you die, your nominee will get the money, that is death benefit. And again, depending upon the type of payment, there are two kinds of policy, that is end of year of death policy and immediately on death policy. Okay, and next we have pure endowment assurance. Pure endowment assurance. Now this is slightly different. Say you buy the policy at X and the term is n years, so this is X plus n. So now in this assurance, you have to survive if you want to get the benefit. Okay, so this is the duration that you have to survive, and when you survived, you'll get the money right at this point, X plus n. So there is nothing called end of year or immediately. All right, now next we have endowment assurance. Endowment assurance. This is the mixture of pure endowment and term assurance. So suppose you buy the policy at X and the term is n years, so this is X plus n. Now if you die within X plus n, so let's say at this point, and if the policy is immediately on death, then your nominee will get the money right at this point. Okay, and if the policy is end of year of death, then at the end of this year your nominee will get the money. And now what if you survive? So if you survive this duration, that is n years, you will get the money. Okay, at this point, X plus n. So this is the mixture of pure endowment and the term assurance. Now next we have deferred assurance. So this is not a different type of assurance, this is simply a different concept. So let's take an example of whole life assurance. In short, I'm writing WLA. So say you buy the policy at age X, and this is X plus N. The duration of deferred period is n years. So this is X plus N. Now if you die within this duration, your nominee will get nothing. But if you die after X plus N, then your nominee will get the money according to the kind of policy. Like if it is end of year of death, then at the end, and if it is immediately, then right at that point. Okay, so you can also consider term assurance in this case, or endowment assurance. Okay, so you can consider several types of assurances in deferred. So this is not a completely different assurance, this is simply just a concept. Okay, now let's look at whole life assurance in depth. So whole life assurance, insert WLA. Now here we are going to consider payable at the end of year of death. We'll also look at immediately on death. So now this is the lump sum cash flow. So lump sum cash flow payable at the end of year of death. And suppose the death benefit, so death benefit is 1 unit. Okay, and the person's age is X. So this is the current age. Now we are interested in calculating the present value of this lump sum cash flow. Okay, now since the policy is end of year of death, so we need to revise the discrete random variable first. Now if you remember, kx is the notation for the discrete random variable. In future lifetime we call cut it future lifetime random variable, right? So here kx means the person's age is X now and he is alive, so how many years he will survive after age X, so that is kx, right? So if kx equals to 0, that means the person will not survive even for a year. So in that case we can say the present value is, so you can consider this is your age and you die within X plus 1. That means, so suppose the policy is here we are considering end of year of death, so you'll get the nominee will get the money at the end, that is X plus 1, right? So to calculate the present value we simply discount it with V, right? So this is simply V, and if kx equals to 1, then this is v square. So this is x plus 1 and x plus 2. So you survive this and you die in between x plus 1 and x plus 2. So the death benefit will be paid at x plus 2, right? That's why this is v square. And similarly you can calculate the other values. So what is kx equals to k? We can say this is v to the power k plus 1, right? So in general we can say that present value is v to the power kx plus 1, all right, where kx equals to 0, 1, 2 up to k. Okay, now we are not interested in present value actually, because we are not sure when the person will die. Okay, that's uncertain. Therefore we are interested in calculating the expected present value. Okay, and now here we'll attach the probability with the discounting factor. So this is summation. Now if you remember the basic idea of calculating the expectation, so whatever is inside the bracket we'll simply multiply that with the PDF or the probability in discrete. So the k ranges from 0 to infinity. Okay, sorry, this is 0 to infinity, this is not k. Okay, so this is infinity. So this is k equals to 0 to infinity v to the power k plus 1, and then the PDF or the probability. Okay, and now k equals to 0 to infinity v to the power k plus 1 and PDF or the probability is kpx qx plus k. All right, we can also write this as k equals to 0 to infinity vk plus 1 k deferred qx. Now this means the person will die within 1 year, but that 1 year is deferred by k units. Okay, now let's see how we can expand this summation. So when you put k equals to 0, you will get vqx, and k equals to 1 v square px qx plus 1. Similarly, k equals to 2 v3 2px qx plus 2, and so on. Okay, now we have a proper actuarial notation for this whole expression, that is ax. All right, now this is just a practice, so you cannot write any other notation, you have to follow this. So the expectation of the present value is ax, and you have to remember this whole expression. Okay, now let's look at the variance. So the variance of present value is expectation of present value square minus expectation of the present value whole square. We know present value is v to the power kx plus 1, so pv square is v kx plus 1, right? So the expectation of the present value square is k equals to 0 to infinity v to k plus 1 and then probability, and we know this is simply ax whole square. Now let v square equals to v1, so this is 1 plus I minus 2, 1 plus I, so this is I dash minus 1. So from this we can say that I dash is 1 plus I whole square minus 1. So now we can write summation k equals to 0 to infinity v1 k plus 1 and then the probability kx equals to k minus ax whole square. So this is nothing but ax operated at I dash minus ax whole square. Okay, now if I dash equals to 1 plus I whole square minus 1 is true, then we have a different notation. Ax at the rate I dash, we can write this as 2ax at the rate I, and you'll find the value of this in the table. I'll show you the table when we do the questions. Okay, so for now you can trust me. So you can find the value of this in the table. So now we can write this as 2ax minus ax whole square operated at I interest rate. All right, and this is the variance of the present value. So this is how you can derive the expectation of the present value and variance of the present value of whole life assurance payable at the end of year of death for death benefit 1 unit. Okay, now let's see for payable immediately on death. So in payable at the end of year of death, we considered discrete random variable because that was happening at the end, right, at the integer ages. But in this case the payment will be immediately, right? So we have to consider the continuous random variable. Now if you remember from the previous video, this is nothing but the exact number of years including fractions the person will survive after age x, right? So the present value is simply v to the power tx, and expectation of the present value is, the idea is again same. Instead of summation we'll use the integration, and we'll integrate this over the whole range, that is from 0 to infinity. So this is 0 to infinity vt and then pdf. So the pdf in continuous is tpx mu x plus t and then dt. Now we have a actuarial notation for this, a bar x. Okay. Now let's consider one assumption. So what happens is, on an average, death occurs during, in between birthdays. So this is shown by the data. Okay. So this is shown by the data. So now let's say, so this is your age x and this is x plus 1. So death usually occurs in between x and x plus 1, and this is shown by the data. All right, and we are going to assume this in our calculation. So now we are considering the immediate payment. So the discounting factor in this case will be v 0.5, right? Or let's say the x is 0 and x plus 1 is just 1. So in this case the discounting factor is 0.5 because the death is occurring at the midpoint and payment is also going to happen at this point. So the discounting factor is v to the power 0.5, and we also need to attach this with the probability, right? Death probability, that is 1qx. Okay. And if death occurs in between 1 and 2, then we need to add the probability of survival for this duration. So this is v to the power 1.5 1px and then qx plus 1. Similarly, v 2.5 2px qx plus 2. Okay, and so on. So now we can say a bar x is approximately equal to v to the power 0.5 1 qx plus v 1.5 1 px plus, this is q x plus 1 plus v 2.5 2 px q x plus 2 and so on. Now let's multiply this with v to the power 0.5 divided by v to the power 0.5. Now let's bring this inside the bracket. So this is v qx plus v square px qx plus 1 v3 2 px qx plus 2 and so on. And this term we can bring this up. So this is 1 plus I 0.5. Okay, now we just solve this. This is nothing but the actuarial notation, that is ax 1 plus I to the power 0.5. Okay, so we can say a bar x is approximately equal to ax 1 plus I 0.5. And please remember, this is based on our assumption. All right, now, and we are going to use this in the variance, so please remember this for now. So now let's see how we can derive the variance of the present value. So the variance is expectation of present value square minus whole square of the expectation of present value, and present value is v to the power tx. So this is integration 0 to infinity v 2t t px mu x plus t dt minus a bar x whole square. Now again we'll use the same strategy, v square equals to v1 and I dash equals to 1 plus I whole square minus 1. So 0 to infinity v1t t px mu x plus t dt minus a bar x whole square. So this is nothing but a bar x at the rate I dash minus a bar x at the rate I, and this is whole square, right? Now here, as I told you, we are going to use this formula. So we know that a bar x is approximately equal to 1 plus I to the power 0.5 ax. All right. Now suppose this is I dash, so this will be I dash, and this is also at the rate I dash. Okay. Now we also know that ax at the rate I dash is equals to 2ax at the rate I if I dash equals to 1 plus I whole square minus 1 is true. So from here we can say that 1 plus I dash is equals to 1 plus I whole square. Now if we replace 1 plus I dash with 1 plus I, then we can go from ax I dash to ax at the rate I, right? So here we can say that a bar x I dash approximately equal to 1 plus I dash 0.5 ax at the rate I dash. So let's replace 1 plus I dash with 1 plus I square. So 1 plus I square to the power 1 over 2, and this will become 2ax at the rate I, right? This is 1 plus I 2ax at the rate I, a bar x, okay, at the rate I dash. All right, and we have a different notation for this. So we write 2 a bar x at the rate I. All right, so this is equals to this, and this is approximately equal. Okay, now using this result we can write 2 a bar x minus a bar x at the rate I, and this is whole square, right? So this will be approximately equal to 1 plus I 2ax at the rate I minus 1 plus I to the power 0.5 ax whole square at the rate I. So this is equals to, let's take 1 plus I common. So 1 plus I 2ax minus ax whole square operated at I interest rate. Okay, so this is the variance of the present value, and we have these values in the table. I'll show you the table later. All right, so this is how you can derive the expectation of the present value and the variance of the present value of whole life assurance payable immediately on death. Okay, so this is all about the whole life assurance. Now let's stop here, and in the next video I'll talk about the term assurance. All right, so I'll see you in the next video. Thank you so much for watching this video.